Welcome folks. So in this video we are going to talk about how we can actually use vectors to solve problems. We have spent several videos now just learning what they are, excuse me, they being vectors, what they are, and how to find their magnitude and how to do arithmetic with them. Let's talk about seeing them in action. So example, you are pulling a koala on a sled behind you and so on some level surface, and let's also assume that there is no friction in this universe, this often fictional universe that we portray a physics problem in, where there is no friction. It wouldn't be too bad if we just added it in, but for simplicity's sake, we'll just ignore it. The rope that you're pulling the sled by makes a 30-degree angle with the ground, and you're pulling the rope with a force of 50 pounds. Okay, so as usual, I recommend drawing a picture, and I think with vectors, it's almost a necessity to draw pictures. So let's do that. So here's my little sled here. Maybe it's got the little track thingy right here. It's like that. And you got your koala. I guess I'll draw it in blue. Like that. It's got a big nose. It looks like that. It kind of looks like a cat, actually. Whatever. Okay, so there's your koala, and then here's you, and you're pulling this thing by a rope. Let's say it's like that. The rope is attached to this guy, and you're pulling it, and the 30-degree angle is with the ground. So we're going to say that it makes this angle right there is 30 degrees. Okay, and remember, the force that you're pulling it at is, well, the force is what makes the rope kind of stay at that angle, so the force vector is actually this vector right here. Let's call that F. I'll call it vector F. Okay, so again, step 0 for any math problem, and is super emphasized for a vector problem, is to draw the picture. You don't have to draw the koala, but you can just draw the vector, and that's fine. Okay, so what does this mean? So let's go back to the question. First question, what is the effective force pulling the koala along the ground? And when I say effective, I'm really just asking for what force is acting on the koala and making it move. What do I mean by that? Well, in this problem, the koala is not going anywhere except in the direction that you're going. Again, you're walking this way. Meaning it's not going up or down, and I guess we're going to assume that from the problem, that the koala is not bouncing up in the air or anything like that. So since the koala only moves to the right, I need to figure out how much force is actually going that way. Not this way, which is where the force vector actually points, but only a part of that force is actually going to pull it this way, to the right. So how could I do that? Well, again, I'll blow up the picture here. So here's the force vector, like so. Here's F, and again, this angle right here is 30 degrees. We can think of any vector that's not, we can think of any vector as having two component vectors because it's drawn in 2 dimensions. If it was 3 dimensions, we could have 3 component vectors. But it's broken up as this vector, and I'll call it F sub x, as you'll often see it, because this is its component in the x direction. And it has some amount going straight up because, again, you're pulling it at some angle. And then we'll call that vector F sub Fy. Alrighty? So again, the koala is not going up into the air, and so the only vector that actually matters into the motion of this koala at the moment is the horizontal component. So we care about this. Okay? So we can always write the actual force vector is the sum of the horizontal component and the vertical component. Right? Again, that's just vector addition right there. Okay. Again, we care particularly about this one at the moment. So the question is, what is F sub x? Well, we know that this is a right triangle, and so we can actually just use what we know about right triangles to figure this out. One thing we do need to know, though, is the length of this hypotenuse. And again, the length of a vector is its magnitude, which we know is 50 pounds. So F sub x we can actually get, well, at least the value of it. The magnitude of f sub x is, well, let's see, this is the adjacent side to the angle, so it's going to be cosine. Whatever the value of the hypotenuse is, or the length of the hypotenuse, times cosine of 30 degrees. We'll just plug in what we know. So we have 50 degrees, sorry, 50 degrees, 50 pounds times cosine of 30 degrees, which is root 3 over 2, I believe. So that ends up being 25 root 3. If I want to actually evaluate this, because it often helps to have an actual value, 25 times the square root of 3 is 43, which, by the way, that should be a check. It should be less than 50, because all 50 of the entire 50 pounds of force is going up in this direction, so only part of it is going horizontally. Is 43.3 pounds. Again, the vector requires a direction as well, and we can just say 43.3 pounds to the right. Or I guess if you drew your vector backwards, you could have drawn it to the left, I suppose. But it's horizontal to the, it's parallel to the ground is the important part. Okay. Alrighty, so the follow-up question is, in theory, if you were pulling this rope hard enough, the koala and the sled would leave the ground, right? So let's think about this. That what's going on is your force is lifting the koala up a little bit, right? Because there is, so again, here's the koala. I'll draw in blue. Oh, why is his head off to the side there? I apologize. Oh my god. With his big nose. Okay. The force that's acting on the koala for you is, or from you, is F sub y, right? We'll just treat the koala as if it is a point, right? But what's holding it down? The reason it's not flying up into the air along with the sled is that there has some, I'll call it W for weight. It weighs something, right? And so it's not going to move unless, so it will be lifted off if the upward force is greater, at least in magnitude, than the downward force. Okay? So here's the question, is when does this happen? Well, we can calculate this by using the same ideas that we just did above. So F sub y, at least the magnitude of it, is equal to the magnitude of F times sine of 30, because it's the opposite side. Let's see, sine of 30 degrees is just 1/2. So that's going to be 25 pounds. Sorry, this is the magnitude of Fy. Okay? So if the koala is less than 25 pounds, it would leave the ground in some fashion. And now again, like, you're pulling it from up here, so since this is a rope and not like a what's the word I'm thinking of? Like a stiff rod or anything like that, it will, again, like, lift up and, like, swing. But the idea, again, this is kind of a force problem perhaps, but I just wanted to see how you can break a vector up into its components, and sometimes, depending on the problem, only a certain component is actually relevant to that particular problem. Okay, so in problem A here, we only needed the horizontal component. In problem B, we only needed the vertical component. Okay, so hopefully that helps, and thanks for watching. In the next video, or we're going to do one more example problem in the next video, so stick around for that. I'll see you there.